I'm gonna need you to raise your glass. I don't care what you put in it. Here's the nights that you can't take back. We live hard, but we love to laugh.
Here we're going to see Grace, and she's about 5'7", which should mean she's about 1.70 meters. And because we're going to be finding potential energy, it's mass times gravity times height. So the value of gravity is 9.8 times 1.7 times 63.5, which is what I guesstimated for her weight, which would mean that she has about 1,062.3 joules of potential energy gravitational. And that means for kinetic energy, which is 1/2 mass velocity squared, she will be having about 5.79 meters per second for her velocity right before she hits the ground with all kinetic energy. And I found this because she will not be losing energy, so she'll have 1,062.3 joules the entire time, and that equals 1/2 63.5 velocity squared. So you just divide by 1/2 63.5 to find that. Here I will be finding the potential energy for Tyler, and he will be the one at the end in a Gray Palmyra volleyball t-shirt. That's the last one to hit in this video. And the equation is still P equals mass times gravity times height. And I estimated his height to be about 1.83 meters because he's 6 feet tall. And I estimated his weight to be 65 kilograms. And then I'm going to multiply that by 9.8, which is the value of gravity. And I get about 1,165.7 joules of potential energy. And then from there, you just plug it in to the kinetic energy formula, which is 1/2 mass times velocity squared, which would get you 1,165.7 equals 1/2 65 times velocity squared. And then after you do the simple algebra from that, you get 39 equals velocity squared. Velocity then equals 5.99 meters per second, and that's about as fast as Tyler will be going right before he lands and hits the ground. Based off of the work that I just did with Tyler and his potential and kinetic energy, which was 1,165.7 joules, we can find out how much work and power that he had when he was hitting the ball. So the work equation is kinetic energy final minus kinetic energy initial, which is basically the change in kinetic energy. So at the beginning, he had no kinetic energy because he had all potential energy. So at the beginning, the initial would be 0. And then the kinetic energy final would be 1,165.7 joules because right before he was about to land, when he had all kinetic energy, all of it was kinetic energy, so it would all have to be that way. And then the work would end up being 1,165.7 joules. And then the power is work divided by time, and I estimated that it took him about 2 seconds to accomplish this task of hitting the ball based off of my knowledge of the game. And his power would then be, power is equal to 1,165.7 divided by 2 seconds, which would end up equaling 582.9 watts of power. Now I'll be finding the potential energy and the kinetic energy of Colin, and he's the one in the black shorts and blue shirt. And because he's a little bit taller, the potential energy should be larger, based off the equation mass times gravity times height. And I estimated his mass to be around 75 kilograms and times 9.8 because that's the constant for gravity, times 1.93 because he's about 6'4", which translates to 1.93 meters. And that gives you about 1,418.6 joules for potential energy gravitational. And then you're going to plug that into the kinetic energy because no energy is lost in this. And that will be 1,418.6 joules equals 1/2 75 times velocity squared. And then with some more simple algebra, you'll get 37.8 equals velocity squared. And then you'll square root both sides to find the velocity for him is about 6.15 meters per second. Now, based off of the final velocity that we found for Colin using energy, we can find the acceleration using kinematics. And then we're going to find that his final position is 0 meters right at the net. His initial position is 3.66 meters, which is about 14 feet off the net. And his final velocity is 6.15 meters per second, which we just found. The initial velocity is 0 meters per second because we found that he's really not moving at the beginning since he has all potential energy. And I still estimated the time to be about 2 seconds. Even though he's starting further off, he's also a little bit taller to cover that distance. And then I used the equation V velocity, final velocity, equals initial velocity plus acceleration times time. The final velocity, 6.15, equals 0, so that's negligible, plus 2a. And then you find that the acceleration is 3.08 meters per second. Then using that, you use the equation final velocity equals, or final position equals initial position plus initial velocity times time plus 1/2 acceleration times time squared. That's a mouthful, but 0, that would be 0 equals 3.66, and then you'll just not even worry about the velocity times time, since the velocity initial is 0, plus 1/2 3.08 times 2 squared. And that comes out to about equaling 3.66 plus 1/2 3.08 t squared. And then once you subtract the 3.66 and then divide by 1/2 3.08, you're going to find like 5.2 is your answer. And then you need to square root that because it's t squared. And you're going to find that your final answer will end up being about 2.2 seconds. And since this is really kind of, I'm estimating a lot of this, it's not going to be exact to the 2 seconds, but it's pretty darn close. So we know that I'm in the right ballpark for this time. And because this time is so close and it's about 0.2 or so seconds off, I know that my acceleration and my other estimated initial and final positions are very close to what they actually were. And I used the acceleration to check myself just to see whether or not I was accurate enough with the information I was giving myself for the equation.
What are you doing? Are you actually videotaping right now? 10, 11.
I hope there's nobody in this class that I know, seriously.
Valued at over $7,000, including rehearsal dinner for up to
Teach me how to do it.
and all-inclusive honeymoon from Cowboy Chocolate.
Melanie!
Leave me alone!
What? This isn't even volleyball.